Research Methods Basics video, we'll be talking about the correlation coefficient. Now, in previous videos, we have thought about and talked about the importance of understanding the relationship between our independent, the x, independent variable, and the dependent variable, or y, dependent variable. Also, we can think of the dependent variable as our outcome variable. That's the one we're most interested in understanding most often. And we're looking at the relationship between these two. Now, we've taken a look at some scatter plots, right? And we've learned about positive and negative relationships as well as curvilinear relationships. You have to have relationships between the variables of interest, or there's no reason to move any further through your research. How do we know, though? Let's say we have a really gigantic data set and we look at a scatter plot and it kind of looks like there's a relationship there, but we're not totally sure just simply because of just how many points there are. How do we know the direction and the strength of the relationship between our variables? Well, we use the statistic called the correlation coefficient. Correlation coefficient. And the correlation coefficient is notated using a lowercase r. That's our correlation coefficient. The correlation coefficient tells us both the strength, how strong the relationship between the two variables is, and the direction of that relationship, whether it's positive or negative. And there are times that we can take a look and suspect a curvilinear relationship. Now, we won't get into that one in this video, but we're just going to be looking at positive and negative relationships using this correlation coefficient. So let's start by taking a look at the equation to get a correlation coefficient. So here we go. We have correlation coefficient R is equal to sample size times the sum of all xy minus the sum of all x times the sum of all y. This is divided by, well, let's not forget these little square root things, the square root of our sample size times the sum of all x squared minus sum of all x squared times the square root of our sample size times the sum of all y squared minus the sum of all y squared. Doesn't that look impressive? But how do we work with it? Well, let's go ahead and think about how we've kind of pulled together figuring out standard deviations and variance. Well, you're going to set up a table just like you would for those things. You just want to make sure that all of these components are easily included, right? So we will have all of our x's in one column. We will have all of our y's in the next column. Then we can have x times y. Then we can have x squared. And we can have y squared. And once we have all of this kind of table filled out, you can put the totals, or your sum of all, kind of in this very last row for each of the columns. And then all you do is go through and plug in these different values. Make sense? That's how you get the correlation coefficient. What would it look like? Well, you may end up with a correlation coefficient. I'm going to go ahead and graph something out here just so you have kind of mental picture. There's our dependent variable, here's our independent variable, and we have something that's really tight like this, lots of points going in this direction. We don't really have any outliers at all. Let's say this correlation coefficient is 0.92. Well, a correlation coefficient, so correlation coefficient ranges from a -1 to a +1, with 0 being no relationship and 1 being perfect relationship, which is really scary because if you see a perfect relationship, you're measuring the same concept with two different variables. And the same holds true with a -1. A perfect negative correlation, it's a problem. But if you have a 0.92, maybe it's about here, that is a strong, right? 0.92, almost a 1 relationship, and it's positive because it is a positive number, right? Now you could have something similar with a negative relationship. But let's say it looks more like this. And let's say that this R is equal to a -0.62. In this case, you could say, a 0.62 is probably going to be, somewhere in here, maybe. You would have a moderate negative relationship. Negative because you have one variable moving up and one moving down. Negative because you have a negative sign here. Moderate because we're, a little more than halfway to perfect, which would be a -1 or a +1. So you have a moderate negative relationship. Never forget that catchphrase that you've probably heard 1,000 times. Correlation does not equal causation, right? There can be so many other variables that are exogenous or endogenous to a relationship. There could be so many other things influencing the variable you're most interested in understanding, your y variable, that a correlation alone does not indicate cause. We can't go much further with inferential statistics if we don't have a relationship. There has to be something going on. But as we get into multivariate and multivariable analyses, that's where we start talking about causal relationships. Correlations, though, tell us if a relationship exists, the direction, and its strength.